In our next section, we're going to look at the verification and troubleshooting of the crypto-map-based LAN-to-LAN VPNs on iOS. And a lot of the techniques that I'm going to show here are also going to carry over into the other variations of IPsec, because again, when you run into a problem with these crypto configs, it's very, very difficult to troubleshoot it based on looking at the show run output. So we want to know what are the different debug commands and what are the different show commands besides show run that we can use in order to try to narrow down what is the specific problem in the configuration. Now, the reason why this is a problem is that there's so many different ways to make minor mistakes in the configuration. We'll see as we get to some of the more complicated configs, especially the remote access VPNs, you may have upwards of 100+ lines of config just for one particular VPN tunnel. So there's so many different ways to make mistakes, and the vast majority of them are going to break your configuration to where the tunnel is 100% non-functional. So understanding how to do the verification is a must, and understanding how to interpret the debug output is a must. So let's talk about what are some of the different commands we can use first to do verification and troubleshooting, and then we're going to take a look at this on the command line. So the first one that we saw previously was the show crypto ISACamp SA. This is going to show the phase 1 security association, which is the ISACamp security association, and this should be in QM idle and have the status active. Where QM idle here means that we have gone into quick mode. Quick mode means to move to the phase 2 negotiation for IPsec. Now, if we see that it is not QM idle, the debug that we're going to look at is either debug crypto ISACamp or debug crypto KMI, which is for the key management. So from here, this is going to show the step-by-step negotiation process. This is one of the debugs that I'm going to walk through step-by-step here and show exactly what do the different pieces mean through the negotiation, and how can we use this to figure out where exactly the problem is in the negotiation process, and is it on the initiator or is it on the responder? Because depending on which end of the connection you're looking at, the sender or the receiver, the debug output is going to be a little bit different here. Now, the other thing for this debug is that if you have multiple tunnels at the same time and you don't want to see the debug for all of them, you can set a debug condition that is going to filter the output to just a specific peer. So let's say I'm on some tunnel head end that's got 100 different tunnels on it, and if you debug crypto ISACamp or debug crypto IPsec, then you're probably just going to crash the box. So you may need to filter through this through based on a specific peer's address, and then that's going to filter out any of the non-relevant output that you're trying to troubleshoot. The next thing that we would want to look at is the authentication working? You can tell this generally from the debug crypto ISACamp whether your pre-shared key or whether your certificates are working, because that's going to be part of the phase 1 negotiation. Also, we want to look at, do the attributes match for the policy? So when we look at this debug for crypto ISACamp, it's going to show the proposal exchange where the initiator says to the receiver, I want to do this authentication, this encryption, this hashing, this Diffie-Hellman group, and then the responder is going to say, I'll check that against my policies and then determine, is this acceptable or is this rejected? And the debug is going to clearly tell you, are the attributes acceptable? And if not, it'll show specifically in the step-by-step process of which attribute is not acceptable or which one is rejected. Now, if everything is working, what we should see is that there is going to be one bidirectional security association for the phase 1 ISACamp. So we should see bidirectional UDP connectivity, UDP 500 specifically, between the initiator and the responder. Now, for phase 2 in IPsec, again, we need to make sure that phase 1 is working first, that phase 1 is active. Doesn't make sense to move on to any of these debugs unless we checked phase 1. So once phase 1 is working, we can look at the show crypto IPsec SA, and we should see that there is an inbound and an outbound security association based on whatever particular transform set that we have. We can also filter this based on the remote address. This is going to show us, are the packets getting encrypted and decrypted? Are they getting encapsulated and decapsulated? This is going to help us to troubleshoot anything that is related to the data plane. So let's say we have an ACL in the transit pack that's dropping ESP, or that's filtering traffic in just one direction. We would be able to see, is the traffic going out but not coming back in? that might be an indication of not necessarily a negotiation problem, but a problem in the data plane. Now, if the Security Association doesn't establish at all, then we would know that's a problem in negotiation. Another place where this could be a problem in negotiation in phase 2 would be with the proxy ACLs. So if the endpoints do not agree that you are sending traffic from A to B, and I'm supposed to send traffic from B back to A, then they're not going to be able to form the phase 2 SA. So we can also see this if we look at the debug crypto IPsec. That's going to show the negotiation of the phase 2 SA. The end result of this should be 2 unidirectional security associations for each proxy ACL entry. So there's going to be an inbound SA and an outbound SA, which again is different than phase 1. Phase 1 has a bidirectional UDP 500 connection. Phase 2 is going to have 2 unidirectional connections. So this means that if we're going through a stateful firewall, we're coming from the outside back in, we have an unsolicited connection that's going to be dropped unless we can get the firewall to either inspect the ESP sessions, or we're poking a hole manually with an ACL to say allow ESP or to allow AH. So let's take a look back at our topology that we're using. And in the previous example, we had a LAN-to-LAN VPN that was set up between router 1 and router 3 that was going between their loopback interfaces. So on router 1, this was 150.1.1.1. On router 3, this was 150.1.3.3. We were using static crypto maps, we were using pre-shared keys, a pretty straightforward policy, and we had connectivity over the tunnel between the 2 endpoints. So now I've introduced some problems in the topology, and without having to look at the show run output, we're going to go through the step-by-step verification and see if we can figure out, what commands do we need to look at and how do we interpret that output to figure out where specifically the problem is in the network. So first, let's start on router 1, and let's try to send traffic between the 2 endpoints. So we're trying to get to the destination 150.1.3.3, and we're sourcing traffic from 150.1.1.1. And we can see the endpoints are unreachable. So something is wrong with the tunnel, but we don't know exactly where. Is it a problem in negotiation? Is it a problem in network address translation? Is it a problem in filtering? From this output, we can't really tell. We just know that something is broken. Okay, so the first thing that we may want to look at then is, did the endpoints negotiate phase 1? So let's look at the show crypto ISACamp SA. Now it says that the SA is in quick mode idle state. So it looks like the negotiation was correct. Let's go ahead and look at the phase 2 SA, show crypto IPsec SA. And we see that we have an inbound security association and we have an outbound security association. So this tells us at least there was negotiation that happened previously for this tunnel, but for whatever reason, something changed and the tunnel is no longer working. So before trying to troubleshoot based on this particular output as it stands, what might be a good idea is to delete the state for the phase 2 SA, delete the state for the phase 1 SA, and see if we can refresh both of them individually. Because what may have happened, it's possible that the tunnel was working at one point, somebody changed something and broke it, but we're not actually going to know that until the tunnel goes to re-key. Because when we look at the output here of the security associations, it says there's still 1,558 seconds left before we re-key, or this amount of data transfer. And if we look at the show crypto ISACamp SA detail, we can also see what is the lifetime of this SA. So this has almost 24 hours left before it's going to re-key. So we don't want to have to wait a day to figure out, is there a problem in negotiation. So let's say clear crypto SA. That's going to delete the phase 2 IPsec SA. And let's clear crypto ISACamp. Okay, that's going to delete the phase 1 SA. Then, of course, we can do it based on specific connection number. This is going to be if we have more than one tunnel currently active. So now let's look at the show crypto ISACamp security association. Right now it says that there's no state because this was deleted manually. So eventually this is going to age out and leave that table. If we look at the Show Crypto IPsec essay, we see that there is no longer an inbound security association, nor is there an outbound security association. So basically right now, the tunnel has been deleted. So let's go ahead and do the pings again and see if we can get phase 1 and or phase 2 to establish. So again, phase 1 verification, Show Crypto IPsec essay, says that there's no state still. Okay, this means that this is definitely not a problem, or at least not up to this point, it's not a problem with anything that is related to phase 2. Now, it's not necessarily to say that there's not a problem in phase 2, but we haven't gotten to that point to even figure that out yet, because the phase 2 negotiation won't occur until IPsec goes into quick mode idle. So we have to troubleshoot up through phase 1 now. So the way that we're going to do this is going to be to look at the debug crypto IPsec. Okay, let's make sure that we're logging to the console. Logging console and logging is on. Okay, so if we do the ping again, ping 150.133 from 150.111, we should see that router 1 attempts to form the tunnel. Because remember, with the crypto map, this is basically a dial-on-demand connection. It says, look at the packet that we're generating. It's going out and interface with a crypto map. If it matches the condition of the crypto map, then we're going to start the IPsec negotiation. Now, in this case here, we see that there's no output from the debug at all. This means that for some reason, the dial-on-demand did not trigger on the crypto map. Okay, there could be a couple different reasons for this. It could be as simple as the crypto map is not applied. Could be that the access list is not applied to the crypto map, or the access list is matching the wrong thing. So let's look at the crypto map configuration. Let's say show crypto map. The crypto map is applied on gig 00, which is our outbound interface, and it says the access list is going to be matching traffic coming from 150.111 going to 150.133. So it should theoretically be triggering the connection, but for some reason it's not. So what other option here is potentially involved in the crypto config? Okay, remember the two things that I mentioned that are independent of crypto that we still need to make sure that are working. One is the routing process, and one is the NAT process. Because encryption happens after routing succeeds, and encryption happens after network address translation succeeds. So before looking at the crypto config, probably what we may want to have done is just look at, do we have a route to the destination? Which in this case, we don't. So something is wrong either with our static routing or something is wrong with our dynamic routing. And let's check the same thing on the other end. Does router 3 have a route back to router 1, which it doesn't? Now, in the previous example, these loopbacks were advertised into EdgeRP. And they were learning their endpoints dynamically through this IGP. But in most designs, this is not really going to be the case, because you're probably forming the IPsec tunnel over a public network like the internet, and the sources and destinations of the traffic in the tunnel is probably private addressing, like the 10 network or the 192.168 network. So this is not going to be something that you could dynamically learn over the tunnel using a crypto map. Now, we'll see later with other designs like the VTI, the virtual tunnel interface, or a GRE tunnel, or a DMVPN, we can run dynamic routing over those. But the vast majority of cases that we are using crypto maps, we're simply going to have to do static routing. Now, the devices in the middle, like the ASA in this case, it does not need a route to the loopback of router 3, and it does not need a route to the loopback of router 1. The reason why is that when packets are sourced from 150.111 and they're going to 150.133, this is then going to get encapsulated inside of ESP, and there's going to be another IP header that the source is going to be the public address of router 1. So now the source becomes 136.118.1, and the destination becomes 136.138.38.3. So we're assuming in this case that the ASA in the middle already has a route to those subnets, because from the ASA's perspective, these are directly connected. So always make sure that you solve the routing process first, because it's completely independent of crypto, both from the initiator and the responder. So on router 1, we would need to make sure that we have a route to 150.133, and we could simply say point that out the gig interface. Okay, under normal circumstances, you would not want to do this because of the way that ProxyARP would have to resolve this, but this is a special case here because we're essentially just pointing it towards the interface with the crypto map applied. Now, no one on the other end actually has to know this destination. We just need to get the traffic to route out the gig interface in order to trigger the crypto map process. And again, this has to do with the issue that the legacy crypto map config is essentially a dial-on-demand VPN. Okay, so we're simply doing static routing, saying that the endpoints of the tunnel are reachable out those connected links. So now when we do the routing lookup, router 3 knows how to get to 1's loopback, and router 1 should know how to get to router 3. We'll see that this is also going to be the case when we're dealing with remote access VPNs, whether it's EasyVPN or whether it's SSL VPN. We need to make sure that when the clients come in and terminate remote access, that we have routing information in order to go back to them. So whether this is static routing or whether this is dynamically through reverse route injection, or it could be something like network extension mode in the case of EasyVPN remote, but still the point remains that routing has to be solved before the crypto process is solved. They're completely independent options here in the network design. Okay, so now that we have the route, let's go ahead and try this again. If we look at the show debug, we're still debugging phase 1. So let's try our ping. Let's see, is this going to initiate the process now? Which it is. Okay, so let's start at the top here and work our way down. Okay, let's undebug this. First thing it says is that we are creating a new peer structure for 136.1.38.3. The peer's port is 500. And notice this is from IPsec. Basically what this is telling us here is that we found what is the destination of the tunnel. The destination of the tunnel is 3. I'm using port 500. That's for our IPsec, and we're going to send them a UDP request. Okay, so this at least means that the crypto map is applied, that routing is working, and that whatever access list we have in the crypto map is triggered against this particular type of traffic. Okay, so now we know we're starting the negotiation. Okay, what we want to do here is see that we have a response back in from router 3. Now from the initiator of the tunnel, we'll see that the output of the debug is going to be different than the receiver or the responder of the tunnel. Now from the initiator, there's not really much that you can tell when you're looking at a failure in negotiation, other than this output here. It says processing of informational mode failed with the peer with this address. This doesn't tell us what the problem is, it's more just saying that there was a problem in negotiation. So to figure out where exactly the problem was, we need to look at the other side. We need to look at the receiver router 3 and look at the same debug on its side, which is going to be again to debug crypto IPsec. Okay, and let's make sure we're logging to the console, and we're logging to the console at level 7. Okay, on router 1, let's go ahead and send those pings again. And on router 3, let's look at the receiving of this. So on router 3, it says we received a packet in from router 1. Destination port was 500, the source port was 500, and we're going to start a new security association. So what does this tell us here was successful? It means that at a minimum, the traffic was able to route from router 1 to 3. So we now know that UDP 500 does not have a transport problem getting from router 1 to 3. Now if router 1 was starting the session but router 3 never received it, we may want to look at the middle and see, is there an access list dropping port 500? Is there a VLAN ACL? Is there some sort of IPS sensor in the middle that's dropping the traffic? But in this case, router 3 did receive the negotiation request. So the transport from 1 to 3 is fine. Okay, next it says we are going to start the proposal process. So we're scanning the profiles. We're checking against our locally configured policies. So this means that router 1 has now proposed that it would like to use triple DES encryption, MD5 hash, Diffie-Hellman group 5, do pre-shared authentication, have the SA lifetime in seconds, and then this is the specific value. Okay, now we can see it says there's a problem here because the encryption algorithm does not match the policy and the attributes are not acceptable. Okay, this is really the final output that you're looking for here. If we have multiple policies that we're checking against, but for some reason the policy does not match, the router or the ASA is always going to end in this output that says the attributes are not acceptable for the phase 1 policy. This tells us that either there's a problem in the encryption, the authentication, the hashing, or the Diffie-Hellman group. Now specifically which one the problem is, it should just tell us right here. It says that the encryption algorithm does not match the policy. Okay, so let's look at what is our policy here and how does that compare with router 1's. So on router 1, let's say show crypto ISACamp policy. And same thing on router 3, show crypto ISACamp policy. Router 1 says I'm doing triple DES encryption. Router 3 says do AES. The rest of the attributes, those are all the same. MD5, pre-shared key, Diffie-Hellman group 5. Now in this case, it's pretty obvious that this is the problem because there's only one policy on both sides. But in a normal design, you're probably going to have a lot of policies, and then you would have to track this debug output all the way down, look at each of the proposals one by one, and then figure out where exactly the attributes do not match in the policy. So here, let's go ahead and change router 1 so that it matches what router 3 is using in the policy. Let's say show run section ISACamp. And this should be here under the ISACamp policy. We want the encryption not to be triple DES, we want it to be AES. Okay, and let's do the debug again on both sides. Debug crypto ISACamp. Debug crypto ISACamp. And make sure we're logging to the console. Now, in a real design, you normally would not want to log this to the console. You probably want to send it to the buffer and then show log to sort through it there, because you can get into a case where this output or this debug just hashes over and over and over, and you can basically lock yourself out of the console. So be careful with that. But here in this case, there's really no other traffic, so it's not a problem. Okay, so let's do the ping. Let's see now what happens on router 1. Router 1 said, and it goes by pretty fast there. You have to pretty much know exactly what to look for. Router 1 said the attributes are acceptable. Okay, this means that they exchanged the policy, so they did the ISACamp proposal, and they agreed on all of the attributes. They agreed they're going to do AES 128, MD5 hash, Diffie-Hellman group 5, and pre-shared authentication. Now, once they have done this and agreed on the attributes, the next step is that they actually do the authentication. So if they're doing pre-shared keys, next thing they would do is to check the passwords. If they're doing PKI, they would check the certificates, exchange their public-private key pairs, and then, or exchange their certificates, I should say, and then check against the trust point to see whether the certificate is valid. Now, whether this has completed or not, we should be able to see this by looking at the Show Crypto ISACamp SA. Still does not say QM idle though, so there's something else wrong here. Okay, if we look at the rest of the output, let's see if we can figure out what happened after we did the proposal. So the attributes were acceptable. We should get to the next process where it says we're going to do the authentication. And it says we're going to do pre-shared authentication. And we're doing main mode key exchange. This is basically where we're trying to authenticate, but you can see that it's attempting multiple times. So this basically says there's a problem in authentication. But you can see from the debug output, it's not very straightforward to figure out that's what the case is. You have to know exactly in the process where does the authentication happen, and if it has a problem, what do you not see and what do you see. So on the initiator here, it basically says we go into main mode key exchange and then we cannot proceed beyond this. Now the output will be a little bit different depending on if you're using pre-shared keys versus certificates. In the case of pre-shared keys, what you want to look at is on the receiver, and the receiver should have this output that says and it's not a very straightforward output. Let's send the packets again. This one here, it says, let me undebug. Crypto ISACamp bad message. The IKE message from router 1 has failed its sanity check or is malformed. What this actually means is that the message came in, it tried to authenticate it, and it couldn't. Now, it doesn't know, is it because there's a problem in the passwords, or is it because someone intercepted the packet and changed it, or there was an actual transmission corruption somewhere in the transit path? Because what the authentication is doing is basically the integrity checking to make sure the person that initiated the packet didn't have someone make any changes in the transit path. Because ultimately, the password that they have configured, the pre-shared key, they're not actually exchanging the password. It's not something that's sent in clear text to say, your password Cisco, my password Cisco, let's authenticate. It's going to be some hashed result of that, and they compare their own local result to the packet that's coming inbound. So at this point, we know that the policy exchange, the proposal exchange was good, but now there's a problem in the authentication. So let's look at the show crypto ISACamp key. This shows simply what is going to be their pre-shared key. So router 1 is using the password Cisco. Router 3 is using the password Cisco, but the problem is this is case sensitive. So lowercase Cisco is not the same as capital. So let's say show run section crypto, and we need to change that. Okay, this should be uppercase. Okay, so next let's do our debug again, debug crypto ISACamp. And let's now try initiating the session again. Okay, still no connectivity, but let's look at the show crypto ISACamp SA. Okay, now we get to QM idle. This means what now? It means phase 1 was 100% correct. So the proposal process for those 4 attributes was good, the authentication was good. Now we move on to phase 2. So we know at least that there's no routing problem between them. There's no problem with the CryptoMap application because it's initiating the connection, and we know that there's no problem in the phase 1 negotiation. So now we would want to check on the receiving side. Does it also have the ISACamp SA, which it should because it's a bidirectional security association. And then we're going to check what's going on with the phase 2 policy. So on router 3, let's look at the show crypto ISACamp SA. It says QM idle. If we also look at the debug output here, we should see that, okay, it says we're doing the pre-shared authentication, and the end result is that the SA authentication status is authenticated. So it means that phase 1 is fine. Okay, now they are going after the after the authentication happens, now we're going to go into quick mode. So it should say we're at quick mode idle. That means phase 1 is complete. we're now going to go to the IPsec negotiation. So this is our phase 2 negotiation. So we can see now router 1 is proposing to router 3, do you want to run ESP-AES in tunnel mode and also do SHA authentication? These attributes are acceptable. So it means that the transform set that they both have configured in the crypto map is equal. Okay, now they're going to go on to the next step, which is to exchange their proxy identities. Proxy identities are the ACL. It says for some reason now the IPsec policy invalidated the proposal. Now what error 32 means, we don't really know. Some of this stuff is only TAC would be able to figure out what exactly the errors mean. But this tells us at least we now know there's some problem with the phase 2 policy. Phase 2 security association policy is not acceptable. So what we need to look at next is the debug crypto IPsec. Because something's wrong with phase 2 now. It's not a phase 1 problem anymore. Debug crypto IPsec. Okay, and let's send the packets again. Okay, on router 3, the receiver, we get to the IPsec proposal. And again, router 1 says, do you want to run AES, ESP-AES with a key length of 128? Do you want to run SHA? And do you want this SA lifetime and tunnel mode? Okay, router 3 says, yes, that's fine. That's what I have configured also. Okay, now we go to exchange the proxy identities. So router 3 is saying that this is my source of the tunnel. The tunnel is going to go to router 1. My local proxy is 150.133. The destination is 150.111. This is basically that access list that we have configured in the transform set. Under this, though, it says that the proxy identities are not supported. Okay, notice this one here. This is an IPsec debug. This is not an ISACAMP debug. What this means is that there's something wrong with the access list between the two of them. So if we now look at the show crypto map, it says that for the pure router 3, the proxy ACL is traffic from 150.111 going to 150.133. So again, if we look at our diagram, when router 1's going that way, it's saying the source should be 150.111. The destination should be 150.133. Okay, this is for router 1's outbound SA. For router 3's outbound SA, the source is going to be 150.133, and the destination is going to be 150.111. So if we look at on router 3 and look at its access list, what's the issue here? Router 3 is saying that the access list is actually the same as router 1's. So the problem is that when we were configuring this, basically the same ACL got pasted in where it should have actually been the opposite. It should have been that the source was router 3's loopback and the destination was router 1's. And again, from the output of the debug here, we can tell that if the proxy ACLs or the proxy identities do not match, then that is going to invalidate the phase 2 policy. So they will not be able to form the tunnel if they do not agree on what is the traffic that is supposed to go inside the tunnel. Okay, so on router 3, let's go ahead and fix that ACL. Let's look at the show run section access list. And basically, this should be opposite. So let's say no permit that and permit it the other way. Source is going to be 150.133. Destination 150.111. Okay, let's try this again now. So from router 3, let's look at now the debug, or let's show debug. Debug crypto IPsec. And initiate the traffic from router 1 again. Now, we don't need to look at the debug crypto ISACAMP because the phase 1 proposal already went to quick mode idle. So we know that it's not a problem with ISACAMP. So let's see now, did they agree on the ACL? So it says the proposal had a proxy match. Okay, this means that they do agree on what the access lists should say. Now you can see also it lists the protocol, the source port, and the destination port. You can get more specific in these access lists and say not only what's the source of the traffic, what's the destination, but I could say the protocol is TCP, the source port is any, the destination port is 80, so that then only my web traffic would go over the tunnel. But we can see here from this output in the debug, this is specifically where they exchange that. So the ACL entries have to be 100% mirror image of each other, otherwise it's not going to accept this. Okay, so now it should say that we're actually going to create the security association. It also tells us what is the protocol. Protocol 50 here means that it is ESP. If this was authentication header, AH, that would say protocol 51. We generate the SPI, which again is like our sequence number, and there's going to be one that is for inbound and outbound. So this is the destination router 3, this is our inbound SA. Destination router 1, this is our outbound SA. So there's 2 unidirectional SAs that have now been created. Okay, so now let's look at, on router 1, did the traffic get through? No. So still something is going on with the tunnel. But we're getting closer. If we look at the show crypto IPsec SA, what do we want to check here? Do we have an inbound SA? And do we have an outbound SA? Yes, we do for both. So this means that negotiation was fine. So if phase 1 negotiation was good, phase 2 negotiation was good, and we formed the tunnels, but we're still not able to send traffic over it, what else could be involved with this? So let's think about what specifically would the traffic flow be. So the first step was that router 1 sent UDP 500 and router 3 returned it. Okay, that is the ISACamp SA. That's bidirectional. Then router 1 sent out the ESP request, so this is our IPsec SA. And then router 3 sent its own request for the IPsec SA. Okay, we're using ESP. ESP is, again, IP protocol number 50. Now we know that UDP did not have a transport problem getting there, because if it did, router 3 would not have received the negotiation to begin with. But what about protocol number 50? Now we could go, of course, to all of the devices in the transit path, like look at the switch here, layer 2, make sure it's not dropping protocol 50. Go to the ASA, make sure that it's not dropping it. But one thing that we can do to kind of narrow this down a little bit further would be to look at the counters for the IPsec SA. So let's say show crypto IPsec SA pipe include, and we want to look at just the NCAP and DCAP. Let's say NCAP pipe DCAP. And let's look at this on both sides. Okay, it says on router 1, we encapsulated 7 packets out the tunnel. They got encrypted and they got hashed. On router 3, we decapsulated those packets. They came inbound, we decrypted them, and we digested them. We then encapsulated 7 of our own packets. They got encrypted, they got hashed, but on router 1, didn't receive it back. So what does this mean then? It means that the packets were able to go this way, but then somewhere on the return they got dropped. These indications in the counters normally means that it's a problem in the data plane. So something is getting filtered in the transit path. Now if we were to look at the ASA, let's go to ASA 4, which is the one in the middle, and let's turn logging on and logging to the console at level 7. And on router 1, let's try to actually send the packets. ASA says I'm denying inbound protocol number 50 coming from router 3 going to router 1, which in this case is our ESP. Now the reason why, if we look at the show name if, the link that is connected to router 1, this is our inside interface. This is security level 100. The outside interface that's going to router 3, that is security level 0. So as we know from the basic stateful filter of the ASA, traffic can go from a higher security level to low and then return, but traffic cannot come unsolicited from a lower security level to a higher security level. And this is the key point that I was trying to make about the IPsec SAs being 2 unidirectional SAs. So it's not a bidirectional request and response, it's a response from one side and a response from the other side, and normally the stateful firewalls in the middle are not going to be able to deal with this. So there's a couple different ways that we could fix this problem. One would just be to go to the ASA and say, don't deny protocol 50. So we could do something like this. We could say, access list outside in permit ESP any. And access group outside in interface, whatever that is, interface VLAN 38. Okay, now on router 1, if we send the pings, we can see now the traffic is going through. Okay, so let's say repeat 100 packets. If we look at our counters now for the NCAP and DCAP, we should see that these are going to be pretty close to each other. Okay, so this is one simple solution that we're just saying don't filter ESP packets as they come in from the outside. But what's the potential problem with this now? We now have an unsolicited hole in the outbound or the outside interface. So we don't know if these ESP packets are a response to a VPN on the inside, or it's just someone randomly sending traffic that's ESP through the firewall. So this might not be the best solution for it. Okay, another better solution might be to say, well, let's get the ASA to actually inspect the packets. So as long as the traffic comes from the inside and is initiated by router 1, then we can inspect the ESP and then allow the return flow to come back in. So let's remove the access list on the interface, and instead, let's say show run policy map. We're going to go to our global policy inspection default and say we're going to inspect IPsec pass-through. IPsec pass-through here means that we're going to try to do a stateful inspection for ESP and for AH. Then if we wanted to do a specific inspection class, this is where you could change the individual options for ESP or AH, like the individual connection limits, the per host limits, but in this case I'm just going to leave them as the defaults. So now if we look at the show connection detail on the ASA, and on router 1, let's clear crypto SA. That's going to delete our phase 2 SA. And let's say clear crypto ISACamp. That's going to delete our phase 1 SA. Then let's reinitiate the tunnel. So ping 150.133 from 150.111. Now if we look at on the ASA and look at those connections, we should see 3 different connections. We have the bidirectional ISACamp flow, which again is UDP 500, and then we have the 2 unidirectional ESP flows. So one of them from 1 to 3, the other one from 3 back to 1. But the difference is now these are being caught by the inspection engine. So we're able now to send traffic from the inside out. We should also be able to send traffic from the outside back in, which we can. Now the main difference is going to be here between inspecting the IPsec versus having the explicit permit in the ACL is that with the inspection, the tunnel is now only going to work if we initiate it from the inside interface. So in this particular case, when we look at the topology here, if we go to router 1 and ping 3, the response is going to come in, and that's fine. Once the tunnel is open, then router 3 can ping router 1 and get a response. But if we were to try to initiate the tunnel from router 3 inbound, the ASA is going to say, well, wait a minute, you're coming from 0, you're trying to get to 100. I'm not going to allow that flow to go through because you're going low security to high. And remember, the inspection engine takes precedence over the security level. So it's basically an exception saying if the connection's there, allow it in. But in this case, the connection doesn't establish unless we go that direction first. And we could see this here if we were to go to router 1 and router 3, and let's delete the connection state. Let's say clear crypto ISACamp, clear crypto SA. And we'll do this on both sides, clear crypto ISACamp, clear crypto SA. Then let's turn logging on the ASA again, logging on. Login console at 7. And we have router 3 try to send packets from the outside in. And actually what I need to do is delete those connections on the ASA. So let's do that again. Let's clear the SAs. Clear crypto ISACamp, clear crypto SA. Show crypto ISACamp SA. Okay, it says phase 1 is deleted. Show crypto IPsec SA. We should see that there's no inbound, there's no outbound SA. So all the state is now deleted for the tunnel. On the ASA, if we show connection detail, these are still waiting to time out. So basically I need to clear all these connections. Clear localhost all. Show connection detail. Okay, so now the connections are deleted. Let's see from router 3, from the outside in, now this traffic is going to get dropped. So if we look at the ASA is now saying you're trying to send UDP 500 from the outside interface to the inside, and since this is not, it does not have an ACL exception, you're trying to go low security to high, I'm not going to allow this inbound. So really, whether this is a valid solution or not really depends on what the requirements are. If the requirements are, we're talking about within the scope of the lab exam specifically, if the requirements are that we need to go to router 3 and ping router 1's loopback, well, no, this is not a valid solution then, because if the tunnel is not initially up, the ASA is going to drop the packets as they come inbound. But if we go to router 1 and do the initiation, then it's going to be fine. Now we'll see with other types of tunnels, if we were to do a GRE tunnel and then run IPsec on top of it, or if we were to run a virtual tunnel interface, or if we were to do something like DMVPN, these tunnels normally would not run into this type of problem because they're not dial-on demand. Or if they are dial-on demand, like in the case of DMVPN, there's always going to be some type of interesting traffic, like our routing protocol Keep Alives, that are going to initiate the tunnel, try to initiate the tunnel from both directions at the same time. But with the CryptoMap, this is one of the limitations that we run into, that it is dial on demand and you might not be able to initiate it from both sides of the connection.